Okay. Yeah, so thank you very much. It's a pleasure to be here. Thanks to the organizers for inviting me. So what I want to tell you about is some recent work that I've been doing over the last year or two, mostly with my PhD student Benjamin Wallisch, but also with my long-term collaborator Daniel Green, who's about to move to San Diego for a faculty position, then with an excellent postdoc, Joan Myers, who's at CETA in Toronto, and then with Matthias Santiago, who's at the IS in Princeton. So the main motivation for us is this beautiful fact, I think, that in the near future, observations in cosmology, CMB, and large-scale structure, have the potential to measure the radiation density in the early universe at about the 1% level. So at the moment we measure radiation density in the early universe at about tens of percent. So this is an order of magnitude improvement in this type of measurement. So what I'd like to ask is, what can we do with such an accuracy? What kind of fundamental physics can we learn if we are able to reach this level of precision? And then more practically, what does it take to get there? So what type of obstacles do these future observations have to overcome in order to make such a measurement a reality? So to the first question, there are many different answers. Of course, I'm going to be describing the most obvious one, is that can help us to identify new light degrees of freedom that are very weakly coupled to the standard model. And I want to say a few words about this kind of search for new relics. Then I want to describe how these new relics can impact CMB and large-scale structure observations and what type of very distinctive signatures they can lead to. So those are the two parts of my talk. I'm going to start off describing the background of particle physics motivations for light relics, and then I'm going to be describing how we can look for them in CMB and large-scale structure, and I'm going to show you some new forecasts that we're doing at the moment for how well we will be able to do in the near and the long-term future. Okay, so let me start describing the theoretical motivation. So in fact, before going to discuss, particles beyond the standard model, it's interesting to just reflect on things, light species that we have in the standard model. And of course, famously, we have neutrinos. They're very weakly coupled in this standard model. They decouple from the rest of the plasma around 1 second after the Big Bang. That leaves a radiation density in the early universe that is about 41%. Okay? So that's a significant contribution to the stress energy tensor in the early universe. So we should be able to measure the gravitational effect of that neutrino energy density. And of course, famously we have, so this has been seen in the CMB anisotropes, has also been seen through the effect on primordial abundances and BBN. So we have measurements of that energy density. And so typically, this energy density is parameterized in terms of this effective number of neutrino species, where an effective of 1 counts exactly 1 standard model neutrino energy density. And any deviation from the expectation of 3 would either correspond to extra relativistic species or change of the standard model neutrino interactions. Okay? So this n effective, for example, can even be negative if somehow the standard model neutrinos don't behave the way we expect them to behave. So this is often called effective number of neutrinos, but it might have nothing to do with neutrinos. Okay? In particular, we can have very small deviations from this value. So at the moment, this n effective is measured at about 10%. We hope to measure it at 1% level, and small deviations can arise from extra light fields. And so those extra light fields can arise, in various extensions of the standard model. And so here I've given a couple of examples. Typically, these particles can be very weakly coupled. So although they're very light, they're hard to produce in terrestrial experiments. However, in astrophysics or in cosmology, we have the benefit of going to very dense environments. So inside of stars or in the very early universe, high densities can overcome small cross-sections. So there can be high production rates, not because the interactions are strong, but because there are high numbers of particles. So even rare processes can be enhanced. And so that's what we're taking advantage of in the very early universe. In particular, what's nice for the cosmological purposes is that we don't have to be very specific about the specific favorite beyond the standard model realization of this idea. The basic phenomenology is described a very simple effective theory that describes how these particles are coupled to the standard model. We can in fact classify these couplings according to the spin of these extra degrees of freedom and the symmetries that protect their masses. And so there's actually a small number of allowed interactions that we can typically write down. In particular, the first thing one finds is that it's actually hard to write down things at low dimension, so marginal and relevant operators of these particles coupled to the standard model are hard, unless these particles are really charged in the standard model gauge groups. These things don't exist. So that explains actually often why these particles are so weakly coupled, because this interaction scale here, lambda, can be high. Okay? And if that's the case, these particles can be more weakly coupled than neutrinos, and they're harder to produce in terrestrial experiments and also a little bit harder to see in cosmology. Okay? Nevertheless, so depending on this interaction strength, this does determine then the expected relic density of this new species, rho of x. Okay? That will become a function of this interaction strength lambda. And particles that are more weakly coupled will have decoupled earlier in the history of the universe and produce a correspondingly smaller relic density. What's interesting, however, is if one takes such a single species that at some point in the history of the universe was in thermal equilibrium and then decoupled at a temperature T decoupling, then it's of course an easy exercise to compute how much density this species produces as a function of its decoupling temperature. The earlier the particle decouples, the smaller this corresponding radiation density. But there's a minimum amount that a single species produces if it just shares its energy density with all of the degrees of freedom of the standard model. Okay? And so that's what's illustrated here for 3 different types of particle species with spin 0, spin 1/2, and spin 1. So one thing to notice from this graph here is that the 2 different regimes, depending on whether the particle decouples before or after the QCD phase transition. So if the particle decouples after the QCD phase transition, then it produces an energy density that's comparable to that of a standard model neutrino. Okay, and that's something that we should have seen, and we haven't. So this regime is highly constrained by things like Planck. Okay, but what you also notice is that there's a second regime where the particle decoupled earlier than neutrinos did. So, and in particular before the QCD phase transition. And then it has a contribution to the total energy density which is reduced by an order of magnitude. And that's just because the standard model has an order of magnitude more the relativistic degrees of freedom before the QCD phase transition than afterwards. Okay? So it's no surprise that we haven't seen these type of particles, but they do produce percent level corrections to the radiation density in the early universe. So it's interesting that we have the opportunity of measuring things at 1%, but then it happens to be a threshold where we would be able to look for the first time 2 times before the QCD phase transition, and a single thermally coupled species would lead to precisely that type of radiation density. So in terms of this parameter ineffective, the minimum amount that the scalar produces happens to be 0.027, and particles with spin would correspondingly produce larger abundances. So that's an interesting number to keep in mind, and an interesting target for future experiments to aim at, I think. In particular, this has become one of the science targets of the next generation of CMB experiments. So we've heard already a lot about efforts of CMB stage 4 to dig into density scalar ratio, but another target is measuring this radiation density very accurately. And one hope is that we can get to levels that would allow us to probe this type of sensitivity. And in fact, even the absence of a detection would be kind of interesting, because it would strongly constrain how strongly these particles could be coupled to the standard model. So this is an example for axions, but there are many other examples like this. Okay, but let me come back to this threshold value of 0.027. So what I want to do in the rest of my talk, how much? 7, okay. So in the last 7 minutes, I want to tell you, in practical terms, what it actually takes to reach this level of sensitivity, and what type of physical effects we can exploit to make such an accurate measurement. So I want to talk about the CMB and also about variant acoustic oscillations. So let's go back to neutrinos and first remind ourselves the type of effects that neutrinos lead to in the CMB. So the main effect that neutrinos have is that increasing the radiation density while keeping this acoustic scale in the CMB fixed will lead to a change in the mean free path of the photons and lead to a change in the damping of the CMB fluctuations. So that's what I've illustrated here, the varying and effective, and you see the varying levels of damping in the CMB spectrum. This effect, however, is degenerate with a change in the helium fraction. So if I change the amount of helium, I'm also changing the amount of free electrons. I also change the mean free path of the photons. That also leads to damping. So there's a famous degeneracy between changing an effective and changing the helium abundance. So until recently, in fact, this was a limiting factor for constraints from the CMB on neutrinos. Okay? However, recently Planck became sensitive enough to measure not just the homogeneous energy density associated with those neutrinos, but also their perturbations. So the neutrinos are fluid with perturbations. These perturbations affect the evolution equations in the CMB. And that leads to a characteristic shift in the phases of the CMB. So this is what I'm illustrating here. So after you remove the damping and also the effect on the frequency of the oscillations, what remains is a shift of the phases here. And so you can see the amount of the shift in this image. And in fact, this effect is quite easy to understand analytically. This was first done in a beautiful paper by Paczynski and Seljak, and then we derived it in our own way a couple of years ago. So if you look at this toy model for the acoustic oscillations in the CMB, you have on the left-hand side the standard oscillator equation, gravitational sourcing on the right-hand side. These metric fluctuations are sourced by all of the matter fluctuations, so photons, baryons, dark matter, and neutrinos. And what's special about the neutrinos is that they're free-streaming particles. So their speed of propagation is the speed of light, while all of the other fluctuations travel at a speed that's at most the speed of photon fluctuations. And it turns out in order to generate a phase shift, you need actually a propagation speed that's faster than the speed of propagation of photon fluctuations. So there's a simple causality argument that inhibits everything else from producing a phase shift, but neutrinos kind of have this unique property that they can travel faster than the photon fluctuations. And that's what generates this phase shift. This phase shift then has even actually been seen. So the effect of neutrinos on the CMB in terms of this phase shift has been isolated and was measured in this nice paper here. So you can see the measurement here. These are very precise measurements of the acoustic peak locations at the delta L of 1. In fact, one neutrino species corresponds to a delta L of 5 shift of the CMB fluctuations, but the data is accurate enough to measure fractions of that shift. Okay? And so that has been measured now. And in the future, we actually have the opportunity of making these measurements an order of magnitude more precise. All right? So this is just an illustration of the amount of improvements to expect when you go from Planck to a version of CMB stage 4. You can expect further improvements if to the CMB data you add large-scale structure data. So of course the same oscillations that we observe in the CMB are also printed in the matter power spectrum. So here's a recent measurement of the baryon acoustic oscillations. Adding extra relativistic species again shifts the phases of these BEO oscillations, and we can look for a similar phase shift in the BEO. What's nice, what we realized recently about this phase shift in the BEO fluctuations is that it's immune to effects of nonlinear evolution. So I think in Ben's classification from yesterday, this is the adapt approach, in the sense that this is a particular observable in large-scale structure that does not evolve nonlinearly. So whatever you compute at linear order is totally preserved on the nonlinear evolution. So it's a very robust way of then extracting early time information from later measurements. And in fact, what we're finding right now is that there's even more information encoded in the specific locations of the peaks, not just the phases. That's robust to uncertainties in the broadband features of the matter power spectrum. And so that gives us a further handle of actually making these measurements more and more precise. So then just as a teaser, we're right now, as we speak, my student in fact is trying to get a sense for how well we will be able to do when you combine current and future CMB with current and future BEO on the value, on the parameter and effective. And so the one result that I'm allowed to show you is the combination of Planck and future BEO in the form of DESI here. So you can see the current Planck constraint in red, and then in green you see the combination of Planck and DESI as a function of the maximum wave number that's included in the BEO analysis. So this, going to the right, this is adding more and more data. And so after we measure the first 4 peaks or so, this levels off because the noise starts to dominate in DESI. But before that happens, in fact, we get a factor of 2 or so improvement over Planck just from the combination with BEO. That's the one I'm allowed to show you because it's the least controversial. When we then combine with future CMB, it gets much more optimistic. Okay, so in particular, when we combine CMB stage 3, something like the Simons Observatory with DESI, we get values of N effective that allow us for the first time to look beyond the QCD phase transition. If we imagine combining CMB stage 4 with future BEO, we in fact get within the reach of this magical number of 0.027. So then let me just put up my conclusions here and take your questions. Thank you very much.